Assalamu alaikum warahmatullah. Now we conclude this chapter with another study case about audio compression. And now linear transformation can be used in audio and video, of course, and before that in image compression as well. So the thing is that here we need to think about the signals as video signal or an image, before that speech signal as a vector in an n-dimensional vector space or subspace. Okay, so we have, let's take a speech signal x. This has n samples. Let's say it has 1000 samples. So x is an vector in the 1000 dimensional space. It's very difficult to store x as it is. Okay, so what they do is that they look for clever ways to represent that subspace using different basis vectors. So actually this subspace can be represented by the canonical or standard basis vectors, which is the unit vector in each dimension, right? But in this, like we said, in this case it will be very difficult or very expensive actually to store this signal. So they look for different bases that span the same subspace that can represent the signal in a more efficient way. One way that is very popular and used in practice is using the discrete cosine transform, which actually builds the basis using this cosine equation. So the signal x of n, which is the speech signal, let's say, can be represented as a weighted sum of cosines. So what we do is that we take those cosines and make up the cosine matrix, or it's called the discrete cosine matrix, and the coefficients are given here. So you have A2, A1, A2, A3, and A4, right? So this is one way to represent the same signal. The thing here is that this mapping takes you from, in this case, from R4 to R4, from R1000 to R1000, for example. Okay, but this transformation has many desirable features. Of course, it's automorphic because it's homomorphic, linear, and bijective. Okay, but the trick here is that this transformation, that if we take this transformation, if we find those A's, not all the A's they have large energy, meaning many of those A's they are close to 0. So if we take 1000 samples, we need to find 1000 A's coefficients, but most of those coefficients are zeros. So it's usually 20% of the energy, more than 20% of the coefficient, they represent 99% of the energy. So 80% of the coefficients, they are very small or negligible, so we can discard them. So we can discard 80% of the coefficients, meaning if we have 1000 coefficients, we can discard 800 coefficients approximately and just keep 200 coefficients. So we compressed the signal from 1000 samples to 2000 to 200,000, sorry, which are the coefficients here. We can say the same thing about images and videos as well, of course, but the technology is a bit more complicated. Okay.